So this week we're putting everything together with our series AC circuits. So I want to just kind of review basically finding current when we have the voltage given across a component. So remember, this is really just Ohm's law, right? So for any component, the current through the component is equal to that voltage drop across the component divided by whatever we're using to describe that component. Okay, so some kind of resistance or reactance in this case, and we're going to call that Z for now, because we're going to talk about something called impedance in just a minute. Okay. So in AC, we're talking about phasors and impedance instead of a direct current signal and resistance, okay? But everything else is going to apply just like you learned in DC. Okay, so let's look at this resistor here in the first part. So we have a 3 ohm resistor, and we have a voltage waveform given to us. And remember what that voltage waveform tells us. It tells us that the peak voltage is 15 volts. It tells us that the phase shift is 10 degrees to the left of the origin. And then we don't really have a frequency here. That's a variable. Okay, so we would get the frequency from that portion of the circuit, but we are given that it's just variable here. So if we want the current waveform, remember the current is going to be whatever the peak current is, sine omega t plus or minus some phase shift. So in order to write that equation, we're going to need to know the peak and the phase shift for the current. So let's talk about how we'll figure that out. Well, first of all, the peak current is just the peak voltage divided by the resistance. Okay, that's just Ohm's law. So we've got 15 volts divided by 3 ohms of resistance, which would mean that we'd have 5 amps of current. Now for theta, for a resistor, theta V equals theta I. Okay, we learned that for a resistive load, the voltage drop across it and the current through it are in phase with each other. So they're going to have exactly the same phase difference. So that means that the phase shift for the current is also going to be that 10-degree shift. So if we want to write the actual equation, that's going to be 5 sine omega t plus 10 degrees. And that would be the current waveform described in that diagram. Now let's talk about what's going on for our inductor. Okay, we've got the same format of our voltage equation, and this time we're given the reactance of our inductor. That's X. Okay, X is reactance. Try to learn that vocabulary. It's going to be helpful to you to know the difference. So reactance there. So the peak current here is going to be the peak voltage divided by the reactance of our inductor. So if we have 56 volts and we divide by 7 ohms, that gives us 8 amps of current. Now for an inductor, remember that the voltage actually leads the current by 90 degrees. So that means if we take our, actually let me write this in terms of our current, because that's what we're looking for. So the current is actually 90 degrees behind our voltage. So if we subtract 90 degrees from our voltage phase shift, which is 10, we get a negative 80. So the current waveform for our inductor in this particular case would be 8 sine omega t minus 80 degrees. And we could sketch this and see what it looks like on the same graph if we wanted to. But we're just kind of working through how to find this right now. Now let's look at our capacitor. So for the capacitor, again, we're given the voltage waveform, which gives us V peak and theta V. We're given our reactance of our capacitor. So the peak current would be V peak over X of C. And we've got 25 volts peak there divided by 100 ohms, or 250 milliamps would be the peak. Now for the capacitor, the current is actually 90 degrees ahead of the voltage, so we would add 90 degrees to the voltage waveform, and the voltage phase shift is -20. So that's a 70. So our current waveform would be 250 milliamps sine omega t plus 70 degrees. Okay, so in everything we're doing, this is really our goal, is to find the resulting current based on the voltage across a component or a series of components. So we're going to apply some of the things we learned in chapter 14 to make this a little bit easier. But essentially this is what we're looking for, is what does that resulting waveform look like? Well, we're going to talk about impedance now. So far we have talked about reactance, and reactance, remember, for a resistor, that's just R ohms. For an inductor, 2 pi f times L gives you the reactance, and the units are ohms. And for a capacitor, it's 1 over 2 pi f times C, also in ohms. Okay, so these we call the reactive elements, and we call X reactance, and R is the resistive element of the circuit, or resistance. So that's going to be important to when we start looking at something we call impedance. Okay, so in DC circuits we talked about resistance. In AC circuits we're going to talk about impedance, because we want to take into account what kind of element we have and how it's going to affect our waveform at the end. Okay, so for the impedance, here I've given you the impedance of all of our main components. So the impedance of a resistor is simply the resistor at 0 degrees. And this is, of course, the polar form. We're going to represent this also in rectangular form, where the impedance of a resistor would be R plus 0 times J. And that should be 0 degrees, not theta. Okay, because the phase shift of the voltage equals the phase shift of the current across and through a resistor. The impedance of an inductor is going to be the reactance at 90 degrees, or in rectangular form, 0 plus X sub L times J. If you were to plug in, for instance, 2 at 90 degrees and then convert that to rectangular form, you would see that that equals 0 plus 2J. Okay. Now for a capacitor, we have the reactance of the capacitor at -90 degrees, and in rectangular form that would be 0 minus X sub C times J. Again, same example. If we had 2 at -90 degrees and you converted that to rectangular form, you would see that that's 0 minus 2J. Okay, and we'll practice with that a little bit. But what you need to know is for series circuits, we sum the impedances just as we summed the resistance in DC. So if we have individual impedances in series, to find the total impedance, we're just going to add them all together. And that's much easier to do in rectangular form than in polar form. So what I'm going to do is, first of all, for number 2 here, I'm going to find the impedance of each of our blocks, so Z1, Z2, and Z3, and then we're going to add them together. So Z1, that's a resistor, so that would be 6 at 0 degrees, or in rectangular form, that's 6 plus 0J. For Z2, Z2 is an inductor, so that's going to be at a positive 90 degrees. So we have 10 at 90 degrees, which is 0 plus 10J. And then for Z3, Z3 is a capacitor. Let me fix that. Z3 is a capacitor, and it's 12 ohms of reactance. So that's going to be 12 at negative 90, which is 0 minus 12J. Now, the total impedance is going to be Z1 plus Z2 plus Z3. So I'm going to leave this in rectangular form and sum that, because in rectangular form, I can just sum the real parts to get the real sum, and I can sum the imaginary parts to get the new sum of the imaginary parts. So for the real parts, I've got 6 plus 0 plus 0. For the imaginary, I've got plus 0J, plus 10J, and minus 12J. So that's a net of minus 2J. And at this point, if you want, we could convert that back to polar form, which would be 6.32 at an angle of negative 18.43. So this is rectangular form, or in your calculator it probably says A plus BI, and this is polar form, which in your calculator is probably RE to the something I or something like that. Okay, so that would be the total impedance of our series network here. So the impedance diagram looks like this chart here at the bottom. So if I were to draw this impedance and put this in a diagram, I'll show you what it would look like. So this is the positive real axis. That's where your resistor, you'll see your resistors in your circuit. This is the positive imaginary, let me fix that, imaginary, which is your inductor or inductive elements. This is the negative imaginary, and that's where you're going to see your capacitor. All right, so for Z1, I'll go back up here to Z1, we have 6 plus 0J. So when I draw that on my axis, that's over 6 and up 0. Okay, so this is my resistor, 6 plus 0J. For Z2, I have a 10 ohm inductor, and it's 0 plus 10J. So I go over 0 and up 10, whoops, over 0 and up 10, and that is my inductor. And then for Z3, that's my capacitor. So I've got 0 minus 12J. So over 0 and down 12. So that would be ZC, 0 minus 12J. And then for my total impedance, 6 minus 2J. So what does that mean? That means I would go over 6. I'm going to draw this with a different color. So I would go over 6 and down 2. So my ZT would be about right here. And this is the impedance diagram. It's really just a matter of graphing the impedance that, that you've calculated in your circuit, so that you see that the total impedance is somewhere between, I guess you would say it's in this third quadrant here, which means it's resistive and capacitive Okay, so it just gives you a little more information about the impedance of your circuit.